Wave-particle duality is one of the most fascinating concepts in quantum physics, capturing the attention of scientists and curious minds alike. At its core, wave-particle duality refers to the phenomenon where particles, like electrons and photons, exhibit both wave-like and particle-like properties, depending on how they are observed or measured. This duality challenges our classical understanding of physics, which typically categorizes entities as either waves or particles, but not both. To illustrate this concept, consider the famous double-slit experiment. When light or electrons are fired at a barrier with two slits and both slits are open, the resulting pattern on a screen behind the barrier resembles an interference pattern, characteristic of waves. This suggests that the particles are behaving like waves, spreading out and interfering with each other. However, if one tries to observe which slit a particle goes through, the interference pattern disappears, and the particles behave like individual particles, creating two distinct bands on the screen. This perplexing behavior raises questions about the nature of reality and the role of the observer in determining the outcome of a quantum event. The concept of wave-particle duality was notably advanced by physicists such as Albert Einstein and Louis de Broglie. De Broglie Einstein proposed that light can be thought of as quantized packets of energy called photons, while de Broglie extended this idea to matter, suggesting that all matter, including electrons, possesses wave-like characteristics. De Broglie's hypothesis was later confirmed through experiments, solidifying the idea that every particle has a wavelength associated with it, defined by its momentum. Wave-particle duality has far-reaching implications, not just in the realm of physics, but also in technology. For instance, the principles of wave-particle duality are foundational to the development of modern electronics and quantum computing. In quantum computers, the superposition of quantum states allows them to process information in ways that classical computers cannot, leading to rapid advancements in fields such as cryptography, material science, and artificial intelligence. Moreover, this duality has prompted philosophical discussions about the nature of reality itself. Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that particles exist in a state of probability until observed, while others, like the many worlds interpretation, propose that all possible outcomes occur, each in a separate branching universe. In summary, wave-particle duality is a powerful concept that not air. Wave-particle duality is a multiple states at once. This phenomenon is known as quantum superposition, and it is one of the fundamental principles of quantum mechanics. To illustrate this concept, think about a spinning coin. While it spins, it isn't just heads or tails. It is in a state of both heads and tails at the same time, until you stop the coin and observe it, at which point it settles into one of the two outcomes. Quantum superposition operates similarly, allowing particles, such as electrons, to be in different energy states simultaneously until they are measured. This principle challenges our usual understanding of reality, as it suggests that particles do not have a definite state until they are observed, leading to various interpretations and discussions among scientists. One fascinating experiment that showcases quantum superposition is the double-slit experiment, where particles like electrons are fired at a barrier with two slits. When both slits are open, the electrons create an interference pattern on the screen behind the barrier, indicating that each electron goes through both slits at the same time, behaving as a wave. However, if a measurement is made to determine which slit the electron passes through, the interference pattern disappears, and the electrons behave like particles, going through only one slit. This experiment highlights the peculiar nature of quantum mechanics, and how observation affects the behavior of particles. Quantum superposition not only has implications for our understanding of the universe, but also has practical applications in technology. For instance, quantum computing relies on superposition to perform calculations much faster than classical computers. In a quantum computer, a qubit can represent both 0 and 1 at the same time, allowing for complex computations to be processed in parallel, which could revolutionize fields such as cryptography, materials science, and artificial intelligence. Moreover, quantum superposition is crucial in the development of quantum technologies like quantum cryptography, which enhances security through the principles of quantum mechanics. In this system, any attempt to eavesdrop on the quantum communication would disturb the superposition state, revealing the presence of the intruder. This ensures that the information remains secure, making quantum cryptography a promising area for future secure communications. Researchers are also exploring the concept of superposition in larger systems, which has led to intriguing discussions about the boundary between the quantum and classical worlds. Some scientists are investigating how macroscopic objects could potentially exist in superposition states, which raises questions about the nature of reality and our perception of it. This exploration of superposition, quantum entanglement, a phenomenon that seems almost magical, occurs when pairs or groups of particles become interconnected in such a way that the state of one particle instantly influences the state of another, regardless of the distance separating them. This peculiar relationship was famously dubbed spooky action at a distance by Albert Einstein, who, despite his monumental contributions to physics, found it difficult to accept the implications of entanglement. When two particles, like electrons or photons, become entangled, measuring one particle's properties, such as its spin or polarization, immediately determines the properties of the other particle, even if they are light years apart. This effect challenges our classical understanding of physics, where objects are thought to act independently unless directly interacting. The implications of quantum entanglement are vast and profound. For example, it holds the key to the development of quantum computers, which promise to solve complex problems much faster than traditional computers. Quantum entanglement also plays a crucial role in quantum cryptography, offering a way to create secure communication channels that are theoretically invulnerable to eavesdropping. When entangled particles are used in a communication system, any attempt to intercept the particles would disturb their quantum state, alerting the communicating parties to the presence of an intruder. Experiments have demonstrated quantum entanglement in various systems, from small groups of atoms to larger, more complex molecules, showing that this phenomenon is not just a theoretical curiosity, but a tangible reality. One of the most famous experiments is the Bell test, which examines the correlation between the measurements of entangled particles. Results from these tests consistently support the predictions of quantum mechanics, reinforcing the idea that entangled particles act in ways that cannot be explained by classical physics or local hidden variables. Additionally, quantum entanglement raises fascinating philosophical questions about the nature of reality and the interconnectedness of the universe. It suggests that the universe may be far more integrated than our everyday experiences imply. For instance, if the properties of entangled particles are linked in such a way that they respond to each other instantly, it challenges our understanding of causality and locality, concepts that are foundational in classical physics. Researchers are also exploring the potential applications of quantum entanglement in fields such as metrology and sensing, where entangled states can enhance the precision of measurements. Quantum sensors, which utilize entangled particles, could revolutionize technologies ranging from GPS systems to medical imaging. In conclusion, quantum entanglement not only represents a cornerstone of the Heisenberg uncertainty principle is a fundamental concept in quantum mechanics, and it introduces a fascinating idea about the limits of our knowledge regarding the properties of particles, proposed by the German physicist Werner Heisenberg in 1927. This principle states that certain pairs of physical properties, known as complementary variables, or canonically conjugate variables, cannot be simultaneously measured with arbitrary precision. A common example of this is the position and momentum of a particle. The more accurately you measure the position of a particle, the less accurately you can know its momentum, and vice versa. This isn't just a limitation of our measuring tools, it's a fundamental property of nature. This principle arises from the wave-particle duality of matter, which tells us that particles such as electrons exhibit both wave-like and particle-like properties. When we try to observe a particle, we interact with it, and this interaction disturbs its state. For instance, if you try to pin down the exact position of an electron, the act of measuring it causes a change in its momentum. This uncertainty is not just a quirky feature of quantum mechanics. It has significant implications for how we understand the behavior of particles at the smallest scales. The Heisenberg uncertainty principle also leads to the idea that particles do not have definite positions and momentum until they are measured. Instead, they exist in a state of probability, where we can only calculate the likelihood of finding them in a certain position or having a certain momentum. This has profound implications for our understanding of reality, suggesting that at a quantum level, the universe is inherently unpredictable. Moreover, this principle is often expressed mathematically through the inequality dx, dp greater than equals h/2, where dx represents the uncertainty in position, dp represents the uncertainty in momentum, and h is the reduced Planck constant, a very small number that sets the scale of quantum effects. This equation highlights that the product of the uncertainties in position and momentum cannot be smaller than a specific value, reinforcing the idea that there is a fundamental limit to what we can know. Interestingly, the Heisenberg uncertainty principle has implications beyond just particles. It has influenced various fields, including philosophy, where it raises questions about determinism and the nature of reality. It suggests that our classical intuitions about certainty and predictability break down at quantum scales, leading to a more complex understanding of the universe. The principle has also inspired various interpretations of quantum mechanics, including the observer effect is a fascinating concept that originates in the realm of physics, particularly in quantum mechanics, and it refers to changes that the act of observation can make on a phenomenon being observed. This idea suggests that simply observing a particle can alter its behavior, which leads to a number of intriguing implications about the nature of reality itself. For example, when scientists attempt to measure the position or momentum of a subatomic particle, the very act of measuring can disturb the particle's state, causing it to behave differently than it would if it were not being observed. This phenomenon challenges our traditional understanding of measurement and reality, as it implies that observers can influence outcomes in ways that are not only unexpected, but also counterintuitive. This concept isn't limited to the microscopic world, as it also finds relevance in various fields, such as psychology and sociology, where the act of observation can affect people's behavior. For instance, when individuals know they are being watched, they may alter their actions or responses, leading to a phenomenon known as the Hawthorne effect, named after a series of studies at the Hawthorne Works plant in the 1920s, where workers improved their productivity simply because they were being observed. This has profound implications for research methodologies, highlighting the importance of considering how the presence of a researcher can impact the results of a study. In the context of everyday life, the observer effect reminds us of the interconnectedness of perception and reality, illustrating how our awareness and attention can shape the world around us. It raises thought-provoking questions about free will, consciousness, and the limits of human understanding, prompting discussions about whether we can ever truly know something without influencing it in some way. This interplay between observer and observed invites us to consider how knowledge and reality are constructed, and it challenges the notion of objectivity in science and philosophy. Moreover, the observer effect has been a subject of philosophical debate, especially in discussions surrounding the nature of reality, consciousness, and the role of observers in the universe. It leads to deeper inquiries about whether reality exists independently of our perception, or if it is, in some sense, a product of observation itself. This idea can be unsettling, as it implies that our understanding of the universe is inherently subjective, colored by our own experiences and perceptions. In the realm of technology, the observer effect also plays a crucial role, particularly in the development of quantum computing and information theory. As researchers delve deeper into the behavior of quantum particles, they are continually confronted with the complexities. Quantum tunneling is a fascinating phenomenon that occurs in the realm of quantum mechanics, and it allows particles to pass through energy barriers, even when they seemingly do not have enough energy to overcome them. Imagine a ball rolling toward a hill. Classically, it would need sufficient energy to reach the top and roll over. However, in the quantum world, particles can behave quite differently. They are not just tiny balls, but rather they exist in a state of probability, which means they can be found in multiple places at once until measured. Because of this, a particle can, in a sense, tunnel through the barrier, appearing on the other side without ever having to climb over it, as though it had found a shortcut through the hill. This concept, which seems almost magical, has real-world implications in various fields including technology and medicine. For instance, quantum tunneling is crucial in the functioning of semiconductors and transistors, which are the building blocks of modern electronics, enabling everything from smartphones to computers. Furthermore, it plays a key role in nuclear fusion, the process that powers the sun and other stars. In the extreme conditions found in the cores of stars, hydrogen nuclei can tunnel through the repulsive force of their positive charges to fuse together and release energy, creating the light and heat that sustain life on Earth. Interestingly, quantum tunneling also has implications for biological processes, such as enzyme reactions, where it has been suggested that tunneling may assist in the efficiency of certain biochemical reactions, allowing organisms to adapt and thrive in various environments. Researchers are continually exploring quantum tunneling, and its potential applications are vast, ranging from the development of quantum computers that leverage tunneling effects to perform calculations far beyond the capabilities of traditional computers, to advances in medical imaging techniques that could improve diagnostic capabilities. As scientists dive deeper into the quantum realm, they are uncovering more mysteries about how tunneling works, its implications for our understanding of the universe, and how it could revolutionize technology as we know it. The bizarre nature of quantum tunneling challenges our classical intuitions about how particles behave, inviting us to rethink the fundamental principles of physics and the very fabric of reality itself. Schrödinger's cat is one of the most famous thought experiments in quantum mechanics, conceived by physicist Erwin Schrödinger in 1935, to illustrate the strange nature of quantum superposition. The experiment presents a scenario where a cat is placed inside a sealed box, along with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the Geiger counter detects radiation, it triggers the hammer to break the vial of poison, which would lead to the cat's death. According to quantum mechanics, until someone opens the box and observes the cat, it exists in a superposition of states, both alive and dead simultaneously. This paradox highlights the complexities and counterintuitive aspects of quantum theory, particularly the role of observation in determining the state of a quantum system. The thought experiment raises profound questions about reality and the nature of observation, leading to various interpretations, such as the Copenhagen interpretation, which suggests that a quantum system remains in a superposition until it is measured. Another interpretation, known as the many worlds interpretation, proposes that all possible outcomes occur, resulting in a branching of the universe into multiple realities. Schrödinger intended his thought experiment to criticize the Copenhagen interpretation, as he believed it led to absurd conclusions. The idea has sparked numerous discussions and debates among physicists and philosophers alike, influencing both scientific and philosophical discourse on the nature of reality. Schrödinger's cat serves as a gateway to understanding quantum mechanics and its implications for our understanding of the universe, prompting us to consider how measurement and observation shape the reality we perceive. The experiment remains a popular topic in both scientific circles and popular culture, symbolizing the mysteries of quantum physics and the challenges of reconciling it with classical physics. Quantum decoherence is a fascinating phenomenon that occurs when quantum systems interact with their environment, leading to the apparent collapse of quantum superpositions into classical states. In simpler terms, it's what happens when the delicate balance of a quantum system is disturbed by external factors, causing it to behave more like the everyday world we experience. This idea is central to understanding why we don't observe bizarre quantum effects, like particles being in multiple places at once, in our macroscopic world. In the quantum realm, particles can exist in superpositions, meaning they can be in multiple states simultaneously. However, once they interact with their surroundings, such as air molecules or even light, these superpositions break down, leading to a state of decoherence. The implications of quantum decoherence are profound, especially in the field of quantum computing. Quantum computers rely on qubits, which can exist in superpositions, allowing them to perform many calculations at once. However, if a qubit interacts too much with its environment, decoherence can ruin the computation, causing errors and loss of information. Researchers are actively working on ways to isolate qubits from their environment to prolong their coherence time, enabling more reliable quantum computations. Interestingly, quantum decoherence also plays a role in understanding the transition from quantum to classical worlds, which raises questions about the nature of reality. Some interpretations of quantum mechanics suggest that decoherence is responsible for the apparent randomness we observe in quantum measurements, as it forces a system into one of its possible states. This has led to debates among physicists about the interpretation of quantum mechanics, with various theories attempting to explain how and why decoherence leads to the classical world we experience. Moreover, decoherence is not just an abstract concept confined to laboratories. It occurs in everyday life, influencing processes such as the behavior of atoms in different states of matter, and even in biological systems. For example, there are studies suggesting that quantum effects might play a role in photosynthesis, and decoherence could affect how energy is transferred in plants. This connection between quantum mechanics and biological processes opens up exciting avenues for research, hinting at a deeper understanding of life itself. In summary, quantum decoherence is a bridge between the quantum and classical worlds, providing insights into why we observe the phenomena we do, while also presenting challenges and opportunities in the field of quantum technology. It serves as a reminder of how interconnected our universe is, blending the strange and counterintuitive aspects of quantum physics with the more familiar aspects of our daily lives. Quantum teleportation, a fascinating concept in the realm of quantum mechanics, refers to the process by which the state of a quantum system, such as a photon or an atom, is transferred from one location to another without the physical transmission of the object itself. This process relies heavily on a phenomenon known as quantum entanglement, where two or more particles become linked in such a way that the state of one particle instantly influences the state of the other, regardless of the distance separating them. This means that when you have entangled particles, Measuring the state of one particle allows you to instantly know the state of the other particle, even if it is light years away. To understand quantum teleportation, it's important to note that it does not involve the teleportation of matter, as seen in science fiction. Instead, it is the information about the state of a particle that gets transmitted. The process generally involves three main steps. First, two parties, often called Alice and Bob, share an entangled pair of particles. Alice then performs a measurement on her particle, which is in an unknown state, and this measurement destroys the original state of her particle. The outcome of this measurement is then sent to Bob through classical communication. Finally, Bob uses this information to perform a transformation on his entangled particle, effectively recreating the original state that Alice had. One of the most exciting aspects of quantum teleportation is its potential applications in quantum computing and quantum communication. In a world where data security is paramount, quantum teleportation offers a method for transmitting information that is theoretically unhackable due to the principles of quantum mechanics. If someone were to eavesdrop on the transmission, the act of measuring the quantum states would disturb them, alerting the legitimate parties to the breach. Moreover, researchers have successfully demonstrated quantum teleportation in various systems, from photons to atoms. In 2017, scientists at the University of Science and Technology of China achieved a remarkable feat by teleporting a photon from Earth to a satellite, orbiting roughly 500 kilometers above, showcasing the long-distance potential of this technology. The future of quantum teleportation is filled with possibilities, including advancements in quantum networks where information could be transmitted instantly across vast distances, or even the establishment of a quantum internet, allowing for ultra-secure communication. However, challenges remain, such as the need for maintaining entanglement over long distances and the efficiency of the teleportation process itself. As scientists continue to explore the many worlds interpretation, often abbreviated as M-Y, is a fascinating concept in quantum physics, and it suggests that all possible outcomes of quantum measurements actually occur but in separate, branching universes. This idea was first proposed by physicist Hugh Everett III in 1957, and it fundamentally challenges our traditional understanding of reality. According to MWI, every time a quantum event happens, like the flipping of a coin or the decay of a radioactive atom, the universe splits into multiple versions, each representing a different outcome. So if you were to flip a coin, in one universe it lands on heads, while in another it lands on tails. This means that all possibilities are realized, and every choice you make or every event that occurs spawns an entirely new universe, which can lead to some mind-bending implications. One key aspect of the many worlds interpretation is its rejection of wave function collapse, a concept in traditional quantum mechanics that suggests a quantum system exists in a superposition of states until it is observed, at which point it collapses into one definite state. In contrast, MWI posits that the wave function never collapses. Instead, it continuously evolves, creating a vast multiverse of interweaving realities. This leads to questions about the nature of consciousness and observation, as it raises the possibility that observers exist in multiple forms across different branches of the multiverse, each experiencing their own unique version of reality. This interpretation also implies that the universe we experience is just one of an infinite number of universes, each with its own distinct history and set of events. This can be quite perplexing, but it also offers a potential resolution to some of the paradoxes in quantum physics. For example, it addresses the famous Schrödinger's cat thought experiment, where a cat in a box is simultaneously alive and dead until someone opens the box. Under the many worlds interpretation, both scenarios occur. In one universe, the cat is alive, and in another, it is dead, effectively sidestepping the idea of a single definitive outcome. Furthermore, the many worlds interpretation has garnered attention not just in physics, but also in philosophy and the study of consciousness. If every possible decision leads to a new universe, it raises profound questions about free will and identity. Are we merely the sum of our choices, existing in a multiverse where every alternative version of ourselves lives out different paths? This concept challenges our understanding. The Copenhagen interpretation is one of the most widely taught and discussed theories in quantum mechanics, named after the city where it was developed, primarily by physicists Niels Bohr and Werner Heisenberg in the early 20th century. This interpretation addresses the fundamental nature of quantum mechanics, focusing on the behavior of particles at the microscopic level, where classical physics seems to break down. One of the key ideas of the Copenhagen interpretation is the concept of wave function collapse. In simple terms, before a measurement is made on a quantum system, the system exists in a superposition of all possible states. It's only when a measurement occurs that the wave function collapses into one of these potential states, determining the outcome. This brings up intriguing questions about the role of the observer in quantum mechanics, suggesting that the act of measurement itself plays a crucial role in shaping reality. Another significant aspect of the Copenhagen interpretation is the idea of complementarity, which posits that objects can exhibit both particle-like and wave-like behavior, but not simultaneously. For instance, light can be seen as both a wave and a stream of particles depending on the experimental setup used to observe it. This duality challenges our intuitive understanding of nature, as it implies that reality is more complex than it appears at first glance. Moreover, the interpretation does not provide a definitive explanation of what happens during the wave function collapse, leading to various philosophical debates about the nature of reality. Critics of the Copenhagen interpretation have proposed alternative interpretations, such as the many worlds interpretation, which suggests that all possible outcomes of quantum measurements occur, each in its own separate universe. This perspective highlights the mystery of quantum mechanics and raises questions about determinism and free will, as well as the nature of existence itself. Despite these debates, the Copenhagen interpretation remains a cornerstone of quantum theory, influencing not only physics but also broader discussions in philosophy, metaphysics, and even consciousness studies. In practical terms, the principles of the Copenhagen interpretation have significant implications in the realm of quantum computing and quantum cryptography, where understanding quantum states and their behavior can lead to groundbreaking technological advancements. The Copenhagen interpretation, with its emphasis on measurement and observation, continues to inspire and challenge scientists and philosophers alike, as they seek to unravel the complexities of the quantum world and its connection to our understanding of reality. This interpretation has not only shaped modern physics, but also invited deeper contemplation about the nature of knowledge and existence. Pilot wave theory, also known as de Broglie-Bohm theory, presents an intriguing alternative to the traditional interpretation of quantum mechanics, which has long puzzled scientists and philosophers alike. This theory, first proposed by Louis de Broglie in the 9920s and later developed by David Bohm, suggests that particles like electrons are guided by a pilot wave, which carries information about their positions and velocities. In this framework, particles have definite positions at all times, which contrasts sharply with the standard Copenhagen interpretation, where particles exist in a state of probability until measured. The pilot wave is described by the wave function, a fundamental concept in quantum mechanics, which evolves according to the Schrödinger equation, ensuring that the behavior of particles is determined by this guiding wave. One of the most captivating aspects of pilot wave theory is its deterministic nature, meaning that if you know the initial conditions of a system, you could predict the future behavior of particles with complete accuracy. This deterministic view raises interesting questions about the nature of reality and the role of observation in quantum mechanics, areas where traditional interpretations often introduce randomness and uncertainty. In pilot wave theory, particles follow trajectories dictated by the pilot wave, and these trajectories can be calculated precisely given the right initial conditions, leading to a picture of the quantum world that is far less mysterious than what many interpretations suggest. Another fascinating implication of this theory is its ability to account for phenomena like quantum entanglement and non-locality, which have baffled scientists for decades. In pilot wave theory, entangled particles are connected through their pilot waves, allowing instantaneous communication between them, regardless of the distance separating them. This notion aligns with Einstein's critique of quantum mechanics, where he famously described such entanglement as spooky action at a distance. However, in pilot wave theory, this spookiness is not something to be feared. Rather, it is a natural consequence of the interconnectedness of particles through their guiding waves. Moreover, pilot wave theory does not discard the probabilistic nature of quantum mechanics entirely. Instead, it offers a refined understanding where the randomness observed in quantum experiments arises from our ignorance of the initial conditions of the particles, rather than from the inherent nature of the particles themselves. This perspective could provide a more intuitive grasp of quantum phenomena, as it aligns with our everyday experiences of causality and determinism. The pilot wave theory also faces challenges and criticisms, particularly regarding its complexity, and the implications of the quantum Zeno effect is a fascinating phenomenon in quantum mechanics, illustrating how the act of observation influences the behavior of particles. Essentially, it suggests that if a quantum system is observed continuously, its state can be frozen, preventing it from evolving or changing as it normally would. This idea emerges from the principles of quantum theory, where particles exist in a superposition of states until they are measured. The effect is named after Zeno's paradoxes, particularly the one that suggests that motion is an illusion, as it poses questions about the nature of reality and how we perceive change. To explain it more simply, imagine a particle that has a chance of decaying or changing state over time. If we observe this particle frequently enough, we can effectively stop it from decaying, because each observation forces the particle to choose its current state, rather than allowing it to transition to another. This phenomenon was first illustrated in an experiment by physicists who used a type of particle called a lambda particle, showing that by measuring it repeatedly, they could inhibit its decay. The implications of the quantum Zeno effect extend beyond the realms of quantum computing and quantum information. In these fields, controlling the state of qubits, which are the building blocks of quantum computers, is crucial. The quantum Zeno effect could potentially be used to enhance the stability of qubits, allowing for more reliable quantum computations. However, the practical application of this effect is still an area of active research, as scientists explore how best to harness it. It's also intriguing to note how this concept challenges our traditional understanding of time and change. In our everyday experience, we observe a continuous flow of time, where things evolve and change without interruption. However, at the quantum level, the act of observation can disrupt this flow, leading to outcomes that seem almost paradoxical. This raises deeper philosophical questions about the nature of reality, perception, and the role of the observer in the universe. The quantum Zeno effect has also sparked interest in various experimental designs, where researchers are looking to test and explore its limits. For instance, experiments involving atoms in traps or other quantum systems are being conducted to see how continuous measurement influences their behavior over time. This ongoing exploration highlights the dynamic and sometimes counterintuitive nature of quantum mechanics, revealing layers of complexity that challenge our intuitive understanding of the physical world. As we delve deeper into the mysteries of quantum mechanics, the quantum Zeno effect Bell's theorem, which was proposed by physicist John S. Bell in 1964, is a fundamental principle in quantum mechanics, that addresses the nature of reality and the concept of entanglement. At its core, Bell's theorem demonstrates that the predictions of quantum mechanics, particularly regarding entangled particles, cannot be reconciled with the idea of local realism, which is the belief that objects have definite properties, independent of measurement, and that information cannot travel faster than the speed of light. The theorem is often illustrated through what are known as Bell's inequalities, which are mathematical inequalities that local hidden variable theories must satisfy. However, experiments conducted to test these inequalities have consistently supported the predictions of quantum mechanics, suggesting that either the world is non-local or that our understanding of reality is fundamentally different than we perceive. One of the most intriguing aspects of Bell's theorem is its implications for the concept of entanglement, where two or more particles become interconnected in such a way that the state of one particle instantly influences the state of another, regardless of the distance between them. This phenomenon has been famously described as spooky action at a distance by Albert Einstein, who was skeptical of the non-local implications of quantum mechanics. The experiments that followed, often involving pairs of entangled photons, have shown violations of Bell's inequalities, indicating that the correlations observed between entangled particles cannot be explained by any local hidden variable theory. The implications of Bell's theorem extend beyond just the philosophical debates about the nature of reality. They also have practical applications in the field of quantum. For instance, quantum key distribution relies on the principles of entanglement and the guarantees provided by Bell's theorem to ensure secure communication. As researchers continue to explore the foundations of quantum mechanics, Bell's theorem remains a cornerstone of our understanding, compelling us to rethink the assumptions we make about the nature of reality, the interconnectedness of particles, and the limits of our knowledge. Moreover, Bell's theorem has led to numerous experiments, with notable ones conducted by Alain Aspect in the 1980s, which provided strong evidence against local hidden variable theories, further reinforcing the quantum mechanical view of the universe. These experiments have become a fundamental part of the discussion surrounding quantum mechanics, entanglement, and the philosophical implications of our understanding of reality. Quantum cryptography, a fascinating and rapidly evolving field, is revolutionizing the way we think about secure communication by using the principles of quantum mechanics to protect information. Unlike traditional cryptography, which relies on mathematical algorithms, quantum cryptography leverages the unique properties of quantum bits, or qubits, to create a level of security that is theoretically unbreakable. One of the most well-known protocols in quantum cryptography is quantum key distribution, or QD, which enables two parties to generate a shared secret key using the behavior of particles like photons. When these photons are sent through a quantum channel, any attempt by an eavesdropper to intercept the communication will disturb the state of the photons, thus alerting the communicating parties to the presence of the intruder. This means that the security of the communication is not based on the difficulty of solving mathematical problems, but rather on the fundamental laws of physics, which makes quantum cryptography incredibly promising for future data protection. As research continues, scientists are exploring various implementations of quantum cryptography, including satellite-based systems which could enable secure communication over long distances. For example, the Chinese satellite Messius has successfully demonstrated QKD over hundreds of kilometers, paving the way for global secure communication networks. Additionally, quantum repeaters are being developed to help extend the range of quantum communication, solving the challenge of maintaining qubit integrity over long distances. The implications of quantum cryptography extend beyond just communication. They could reshape industries that rely heavily on data security, such as finance, healthcare, and national defense. With the advent of quantum computers, which could potentially break traditional encryption methods, the need for quantum-resistant solutions is becoming more urgent. Researchers are also investigating how to integrate quantum cryptography with existing classical systems, creating hybrid models that take advantage of both technologies. Nonetheless, there are still significant challenges to overcome before quantum cryptography becomes mainstream, including the technical difficulties of creating and maintaining quantum states, as well as the high costs associated with the technology. Moreover, the understanding of quantum mechanics itself can be quite complex, which poses an additional barrier to widespread adoption. Despite these challenges, the excitement surrounding quantum cryptography is palpable, as it represents a frontier of science that combines cutting-edge technology with fundamental physics, offering the potential for a more secure digital future. As this field continues to advance, it might not only change how we protect our data, but also how we understand the very nature of information itself, leading to new discoveries. Quantum computing, a fascinating field of study, is revolutionizing the way we think about computation, as it harnesses the principles of quantum mechanics, a branch of physics that explores the behavior of matter and energy at the smallest scales. Unlike traditional computers, which use bits as the smallest unit of data, quantum computers use quantum bits, or qubits, which can exist in multiple states simultaneously, a phenomenon known as superposition. This unique property allows quantum computers to perform complex calculations much more efficiently than classical computers, especially for problems that would take an impractical amount of time for traditional systems to solve. Another intriguing aspect of quantum computing is entanglement, a phenomenon where qubits become interconnected in such a way that the state of one qubit can depend on the state of another, no matter the distance between them. This means that changes to one qubit can instantaneously affect its entangled partner, creating a powerful resource for quantum algorithms. By leveraging superposition and entanglement, quantum computers can tackle problems in cryptography, optimization, and material science that are currently beyond the reach of even the most powerful classical supercomputers. The potential applications of quantum computing are vast and varied, ranging from drug discovery, where researchers can simulate molecular interactions at an unprecedented level of detail, to enhancing artificial intelligence by enabling faster processing of large datasets. Companies like IBM, Google, and startups around the world are racing to develop practical quantum computers, with each step forward in hardware and algorithms bringing us closer to realizing these potential applications. However, there are significant challenges to overcome before quantum computing can achieve its full potential. One of the main hurdles is qubit stability, as qubits are highly sensitive to their environment, and even the slightest disturbance can lead to errors in calculations. This issue, known as decoherence, requires sophisticated error correction techniques and innovative designs to maintain qubit integrity long enough to perform meaningful computations. Researchers are exploring various materials and techniques to create more stable qubits, including superconducting circuits and trapped ions, each with its own set of advantages and challenges. As we continue to unravel the mysteries of quantum computing, ethical considerations also come into play. The ability to break traditional encryption methods poses serious implications for data security, requiring new strategies to protect sensitive information. Additionally, the environmental impact of building and maintaining quantum computers is an important topic for discussion, as the energy consumption and resource demands of these advanced technologies could shape their future development. In educational settings, the rise of quantum computing. Quantum dots are fascinating. Nanometer-sized semiconductor particles that have unique optical and electronic properties, which make them incredibly useful in various fields, including electronics, medicine, and renewable energy. These tiny dots, typically measuring between 2 and 10 nanometers in diameter, can emit light of different colors depending on their size, which is a property known as quantum confinement. When light hits these quantum dots, they absorb photons and then re-emit them at specific wavelengths, allowing for a broad spectrum of colors. This size-dependent emission makes quantum dots ideal for applications such as displays, where they can produce vivid colors, and in medical imaging, where they can be used as fluorescent markers to help visualize cellular processes. One exciting application of quantum dots is in the realm of solar energy. Researchers are exploring how these tiny particles can improve the efficiency of solar cells by allowing them to absorb a wider range of the solar spectrum. By incorporating quantum dots into solar panels, scientists hope to create more efficient devices that can convert sunlight into electricity more effectively than traditional silicon-based cells. Additionally, quantum dots can be used in LEDs, leading to more energy-efficient lighting solutions and displays. The use of quantum dots in these technologies could revolutionize how we harness energy and use light in our daily lives. In the field of medicine, quantum dots are being studied for their potential in targeted drug delivery and cancer treatment. Because of their small size and the ability to attach to specific molecules, quantum dots can be engineered to target cancer cells directly, carrying drugs only to those cells and minimizing damage to healthy tissue. This targeted approach is especially important in cancer therapy, where it is crucial to limit side effects. Furthermore, quantum dots can be used in imaging techniques such as in vivo imaging, allowing doctors to see how tumors respond to treatment in real time, which could lead to more personalized and effective treatment plans. Moreover, scientists are also investigating quantum dots for their potential use in quantum computing. Quantum computing relies on the principles of quantum mechanics, enabling computers to perform complex calculations at speeds far beyond those of traditional computers. Quantum dots can serve as qubits, the fundamental units of information in quantum computing, which could lead to breakthroughs in processing power and data handling, impacting various sectors from quantum dots to artificial intelligence. As research into quantum dots continues, the scientific community is also addressing important challenges related to their use, including toxicity and environmental impact. Some quantum dots contain heavy metals, which raises concerns about their safety if released into the environment or used in consumer. Quantum field theory, often abbreviated as QFT, is a fundamental theoretical framework in physics that blends quantum mechanics with special relativity, providing a comprehensive description of how particles interact and behave at the most basic level. At its core, QFT treats particles not as individual entities, but as excited states of underlying fields that permeate the universe, which means that every type of particle, such as electrons or photons, corresponds to a specific field. This concept can be quite mind-boggling, as it challenges our everyday understanding of particles being distinct, solid objects, rather than manifestations of fields that can exist in different states. One of the key insights of QFT is that these fields can fluctuate, creating virtual particles, which are fleeting, temporary particles that appear and disappear in a vacuum, as permitted by the principles of quantum mechanics. This phenomenon is essential for understanding forces in nature, such as electromagnetism and the strong nuclear force, as these forces are mediated by particles. For instance, the electromagnetic force is mediated by photons, which are the quanta of the electromagnetic field, highlighting how the interactions between charged particles, like electrons, are fundamentally rooted in the properties of these fields. The invention of QFT was a significant milestone in the development of modern physics, as it led to the formulation of the Standard Model, which is a well-established theory that explains how 3 of the 4 fundamental forces of nature, electromagnetic, weak, and strong forces, operate, along with the particles that make up matter. Although the Standard Model has been remarkably successful in predicting experimental results, it does not incorporate gravity, which is addressed by general relativity, creating a challenge known as the quest for a unified theory. One fascinating aspect of QFT is the concept of renormalization, a mathematical process that removes infinities from calculations, allowing physicists to make meaningful predictions about particle interaction. Even though this process can seem somewhat abstract and counterintuitive, it has proven to be incredibly effective in producing accurate results. For example, through renormalization, physicists have calculated quantities like the magnetic moment of the electron with astonishing precision, matching experimental measurements to an extraordinary degree. Moreover, QFT has broad implications, not only in particle physics but also in areas such as condensed matter physics, where it helps explain phenomena like superconductivity and the behavior of materials at extremely low temperatures. This versatility demonstrates the power of QFT as a tool for understanding complex systems and diverse physical phenomena. Fermions and bosons are two fundamental classes of particles in the universe, and understanding their differences is crucial for grasping the basics of quantum physics. Fermions, named after the physicist Enrico Fermi, are particles that follow the Pauli exclusion principle, which means that no two identical fermions can occupy the same quantum state simultaneously. This principle is why electrons, protons, and neutrons, which are all fermions, form the building blocks of matter. They cannot simply stack up in the same space and state. This behavior leads to the formation of the structure of atoms, and it is essential for the stability of matter as we know it. On the other hand, bosons, which are named after the physicist Satyendra Nath Bose, do not follow the Pauli exclusion principle. Instead, they can occupy the same quantum state as other bosons. This property allows bosons to clump together, leading to phenomena such as superconductivity and superfluidity. One of the most well-known bosons is the photon, which is the particle of light, and it plays a crucial role in electromagnetic interactions. Another significant boson is the Higgs boson, a particle that gives mass to other particles through the Higgs field, a key concept in the standard model of particle physics. The distinction between fermions and bosons doesn't just stop at their statistics. It also affects the way they interact with each other. Fermions tend to form matter and build up structures, while bosons often mediate forces. For example, gluons are bosons that mediate the strong force which holds quarks together inside protons and neutrons. This interaction is vital for the stability of atomic nuclei. Furthermore, the difference in spin is another defining characteristic between these two classes of particles. Fermions have half-integer spins, like 1/2 or 3/2, while bosons have integer spins, like 0 or 1. This difference in spin leads to very different behaviors in quantum mechanics. For instance, at extremely low temperatures, a group of bosons can occupy the same quantum state, forming a state of matter called a Bose-Einstein condensate, where quantum effects become apparent on a macroscope. In contrast, fermions at low temperatures fill available energy states up to a certain limit, creating what is known as the Fermi sea. In summary, while both fermions and bosons are essential to the understanding of the Pauli exclusion principle, is a fundamental concept in quantum mechanics, introduced by the Austrian physicist Wolfgang Pauli in 1925. It states that no two fermions can occupy the same quantum state simultaneously within a quantum system. Fermions are particles, such as electrons, protons, and neutrons, which have half-integral spins, and this principle is crucial for understanding the behavior of matter at the atomic level. A striking consequence of this principle is the structure of the periodic table, which is shaped by how electrons fill atomic orbitals in an orderly fashion, leading to the diverse chemical properties of elements. When we think about electrons in an atom, each electron has a unique set of quantum numbers that describe its specific state, including its energy level, angular momentum, and magnetic moment. This means that in an atom, no two electrons can have the same set of quantum numbers. For example, in the case of helium, which has 2 electrons, they occupy the lowest energy level, but one spins in the opposite direction to the other, allowing them to coexist in the same orbital. This arrangement helps to explain why helium is a noble gas, as its electron configuration is complete and stable, making it less likely to react with other elements. The principle also plays a vital role in the stability of matter. Without the Pauli exclusion principle, electrons would not have the restrictions that prevent them from collapsing into the nucleus, as they would all occupy the lowest energy state available. This would lead to atoms that are vastly different from what we observe today, potentially resulting in a universe where complex structures, such as stars, planets, and ultimately life itself, could not form. Additionally, the Pauli exclusion principle is the reason why solids have their characteristic structures and properties. In metals, for example, the electrons are not tightly bound to individual atoms and can move freely, which allows for electrical conductivity. In contrast, in insulators, the electrons are more localized, preventing them from conducting electricity. The principle also underpins the behavior of neutrons in atomic nuclei, influencing how they pack together, which is essential for the stability of various isotopes. Moreover, the Pauli exclusion principle has implications in many areas of physics, including the phenomenon of electron degeneracy pressure, which is a crucial factor in the stability of white dwarfs. When a star has exhausted its nuclear fuel, it can no longer support itself against gravitational collapse. However, the electrons in the star's the Planck length, a concept that emerges from the realm of quantum mechanics and cosmology, is regarded as the smallest measurable unit of length in the universe, measuring about 1.6 times 10 to the power of 35 meters. This minuscule scale is derived from fundamental constants including the speed of light, the gravitational constant, and Planck's constant, which altogether create a framework that defines the limits of our understanding of space and time. At this scale, the classical ideas of gravity and space-time begin to break down, leading physicists to speculate about the nature of the universe at its most fundamental levels. The Planck length suggests that, below this threshold, the smooth fabric of space-time might become grainy or foamy, which raises fascinating questions about the very structure of reality itself. In the context of string theory, the Planck length plays a crucial role, as it is theorized that fundamental particles are not point-like objects but rather tiny vibrating strings, whose sizes are on the order of the Planck length. This leads to intriguing implications for the nature of matter and forces, as these tiny strings could unify the 4 fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single framework. Moreover, the significance of the Planck length extends into discussions about black holes, where it is believed that the density of matter and energy can become so extreme that the conventional laws of physics cease to apply. In these extraordinary conditions, the concept of the Planck length might provide insights into the quantum behavior of black holes and how they emit radiation, known as Hawking radiation, which was proposed by physicist Stephen Hawking. As scientists delve deeper into the quantum realm, they are also exploring the implications of the Planck length for theories of quantum gravity which seek to reconcile general relativity with quantum mechanics. This pursuit has led to various approaches such as loop quantum gravity and causal dynamical triangulation, which attempt to describe how spacetime behaves at or below the Planck scale. Experiments designed to probe these fundamental questions are incredibly challenging, given that current technology operates at scales much larger than the Planck length. However, researchers are optimistic that advancements in particle physics and observational astronomy may one day provide indirect evidence about the nature of space-time at this incredibly small scale. The mysteries surrounding the Planck length continue to inspire scientists and philosophers alike. Prompting profound inquiries into quantum gravity is a fascinating area of physics that seeks to unify the principles of quantum mechanics which governs the behavior of the very small, with general relativity, which describes the force of gravity on a cosmic scale. This quest is important because, while we have a solid understanding of how gravity works in large-scale structures, like planets and galaxies, the behavior of gravity at the quantum level remains a mystery. One of the main challenges in this field is that gravity is incredibly weak compared to other fundamental forces, making it difficult to observe its effects at the quantum level. Scientists have proposed several theories to address this, including string theory, which suggests that the fundamental particles we observe are actually tiny vibrating strings, and loop quantum gravity, which attempts to describe space and time as a network of discrete loops. These approaches not only aim to explain how gravity operates at microscopic scales, but they also have implications for our understanding of black holes, the Big Bang, and the very fabric of space-time itself. For instance, in loop quantum gravity, it is theorized that space-time might be quantized, meaning that there are smallest possible units of space and time, similar to how matter is made up of atoms. This idea challenges traditional notions of a smooth continuum of space and time, suggesting instead that the universe is made up of tiny, indivisible chunks. Another interesting aspect of quantum gravity is the concept of entanglement, where particles become interconnected in such a way that the state of one can instantly affect the state of another, regardless of the distance separating them. This phenomenon raises intriguing questions about the nature of space, time, and gravity itself, potentially leading to insights into how these forces interact at the quantum level. Moreover, researchers are also exploring the implications of quantum gravity for our understanding of the universe's origins. For instance, if space-time is quantized, could it suggest a different scenario for the beginning of the universe than the traditional Big Bang model? Some scientists propose that the universe might have undergone a series of cycles, bouncing back from previous states, and that the quantization of space-time could play a role in these transitions. It's a tantalizing possibility that opens the door to new theories about the universe's history and structure. In addition to theoretical advancements, experimental efforts are ongoing to test the predictions of quantum gravity. Some of these experiments involve observations of cosmic rays, gravitational waves, and the behavior of particles in high-energy collisions, all of which could provide insights into how gravity operates. Dark matter, a mysterious substance that makes up about 27% of the universe, is one of the most intriguing topics in modern astrophysics. It does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter, such as stars and galaxies. Scientists theorize that dark matter exists because of the observed discrepancies between the mass of galaxies and the mass calculated from their visible components, revealing that something unseen must be influencing their formation and movement. The leading candidates for dark matter include weakly interacting massive particles, or WIMPs, which are predicted to interact only through gravity and possibly the weak nuclear force. Yet, despite extensive searches, these particles have not been directly detected. Quantum mechanics, on the other hand, is a branch of physics that deals with the behavior of particles at the smallest scales, such as atoms and subatomic particles, introducing concepts that often defy our everyday experiences. For instance, particles can exist in multiple states at once, a phenomenon known as superposition, and they can also be entangled, meaning the state of one particle is directly related to the state of another, no matter how far apart they are. The combination of dark matter and quantum mechanics leads to fascinating questions about the nature of reality, as some researchers propose that dark matter could be explained through quantum theories, suggesting that it might consist of particles that behave according to quantum rules, leading to potential breakthroughs in our understanding of both the universe and the fundamental laws of physics. One intriguing aspect of dark matter is its potential connection to dark energy, which makes up about 68% of the universe and is believed to be responsible for the accelerated expansion of the universe. Researchers are exploring whether dark matter and dark energy could be manifestations of a deeper underlying theory, possibly linked by quantum field theories that have yet to be fully understood. In this context, some physicists are investigating modified theories of gravity that might provide alternative explanations for dark matter's effects, leading to an exciting interplay between quantum mechanics, general relativity, and cosmology, as these fields collide to offer new insights into the fabric of the universe. Moreover, experiments like the Large Hadron Collider and various underground laboratories are designed to hunt for dark matter particles, while quantum experiments, such as those involving quantum entanglement and superposition, are pushing the boundaries of our understanding of how particles interact on a fundamental level. This ongoing research brings a sense of urgency to the quest for knowledge. As scientists strive to non-locality is a fascinating concept that emerges from the field of quantum mechanics, fundamentally challenging our understanding of how particles interact across distances. At its core, non-locality suggests that two particles can be connected in such a way that the behavior of one instantly influences the behavior of the other, regardless of the space that separates them. This idea was brought to the forefront of scientific discussion through the work of physicist Albert Einstein, who famously referred to it as spooky action at a distance. In a well-known thought experiment, Einstein, along with his colleagues Podolsky and Rosen, proposed what is now called the EPR paradox, questioning whether quantum mechanics provides a complete description of physical reality, given that entangled particles seem to defy the conventional rules of locality. The concept of non-locality gained empirical support through experiments involving entangled particles. When particles, such as photons, are entangled, measuring the state of one particle immediately gives information about the state of the other particle, even if they are light years apart. This phenomenon was famously tested in the 1980s by physicist Alain Aspect and his team, whose experiments confirmed that the results of measurements on entangled particles were correlated in ways that could not be explained by classical physics or local hidden variable theories. The implications of these findings are profound, suggesting that the universe may be interconnected in ways that defy our everyday experiences and intuitions about space and time. Non-locality raises intriguing questions about the nature of reality itself. It suggests that information can be shared instantaneously, without regard to distance, challenging our traditional notions of cause and effect. While this may sound like science fiction, it has real implications for fields such as quantum computing and quantum cryptography, where the principles of non-locality can be harnessed to create secure communication systems and powerful computational methods. Furthermore, non-locality has sparked discussions about the potential for a deeper understanding of the universe, leading some physicists and philosophers to explore ideas about a connected consciousness or a universal field that links all matter. However, despite its intriguing nature, non-locality does not allow for faster-than-light communication or the transmission of information in a way that would violate the principles of relativity. Instead, it suggests that our classical intuitions about separateness and distance may not fully capture the complexity of the quantum world. This has led to various interpretations of quantum mechanics, including the Copenhagen interpretation, which embraces the probabilistic nature of quantum events, and the many worlds quantum fluctuations, a fascinating phenomena that occur at the subatomic level, where the principles of quantum mechanics govern the behavior of particles. In simple terms, quantum fluctuations refer to the temporary changes in energy that happen in empty space, leading to the creation and annihilation of particle-antiparticle pairs, even in a vacuum. This means that, despite appearing empty, a vacuum is actually teeming with activity, as particles pop in and out of existence for incredibly brief moments. These fluctuations are a fundamental aspect of quantum field theory, which describes how fields interact with particles. One of the most intriguing implications of quantum fluctuations is their role in the early universe. During the Big Bang, it is believed that quantum fluctuations played a crucial part in the formation of large-scale structures like galaxies. These tiny variations in energy density led to the gravitational clumping of matter, giving rise to the universe as we know it today. The concept of inflation, a rapid expansion of space in the early universe, further emphasizes the importance of quantum fluctuations, as they provided the seeds for the cosmic structure we observe. Moreover, quantum fluctuations are not just an abstract concept. They have real-world implications, particularly in the realm of quantum computing and quantum cryptography. In quantum computing, the principles of superposition and entanglement allow qubits to exist in multiple states simultaneously, potentially leading to a new era of computational power. Quantum fluctuations can introduce noise into these systems, which researchers need to manage to ensure accurate calculations. In the realm of theoretical physics, quantum fluctuations also contribute to the phenomenon of Hawking radiation, proposed by Stephen Hawking. This radiation suggests that black holes are not entirely black, but can emit particles due to quantum effects near their event horizons. As a result, black holes can gradually lose mass and eventually evaporate, which challenges our understanding of their nature. Additionally, quantum fluctuations have been linked to the Casimir effect, where two uncharged parallel plates placed very close together in a vacuum will experience an attractive force due to the restrictions placed on the quantum fluctuations between them. This effect has been experimentally verified and demonstrates how vacuum energy can have tangible effects in physical systems. The world of quantum fluctuations is also a topic of ongoing research and debate. Physicists are investigating how these fluctuations might lead to new insights in areas like dark energy and the fundamental nature of reality itself. Some theories propose that quantum fluctuations could have implications for the multiverse hypothesis, suggesting that our universe might be just one of many. The quantum harmonic oscillator is a fundamental concept in quantum mechanics, serving as a model for a wide range of physical systems. Essentially, it describes a particle that is subjected to a restoring force proportional to its displacement from an equilibrium position, much like a mass on a spring. In quantum mechanics, this idealized model allows us to explore the behavior of particles at a subatomic level, where classical physics no longer applies. The energy levels of the quantum harmonic oscillator are quantized, meaning that the particle can only exist in specific energy states, which are determined by the equation E_n equals n plus 1/2 ho, where n is a non-negative integer, h is the reduced Planck's constant, and o is the angular frequency of the oscillator. This quantization leads to fascinating phenomena, such as zero-point energy, which is the lowest energy state of the system, indicating that even in its ground state, the oscillator possesses a certain amount of energy, due to the inherent uncertainties in quantum mechanics. One of the remarkable implications of the quantum harmonic oscillator is its ability to explain various physical systems, including molecular vibrations, phonons in solids, and even the behavior of electromagnetic fields in a cavity. This broad applicability makes it a cornerstone of quantum theory, and it is often used as a teaching tool for students learning about quantum mechanics. The mathematical framework of the quantum harmonic oscillator involves the use of wave functions, which describe the probability amplitude of finding a particle in a particular state. These wave functions are solutions to the Schrödinger equation, and they exhibit unique properties such as being orthogonal and normalized, which are crucial for understanding the behavior of quantum systems. Another interesting aspect of the quantum harmonic oscillator is its connection to the field of quantum field theory, where particles are treated as excitations of underlying fields. In this context, the oscillator model helps explain how particles like photons can exist as quantized excitations of the electromagnetic field. Furthermore, the techniques used to analyze the quantum harmonic oscillator, such as ladder operators and creation and annihilation operators, have been instrumental in developing more complex quantum theories. In real-life applications, the principles derived from the quantum harmonic oscillator can be seen in technologies like lasers, where the quantization of energy levels leads to the emission of coherent light. Additionally, understanding the behavior of quantum harmonic oscillators is essential in the field of quantum computing, where qubits can be modeled as oscillators, allowing for the manipulation of information at incredibly small scales. Quantum electrodynamics, often abbreviated as QED, is a fundamental theory in physics that describes how light and matter interact. It combines the principles of quantum mechanics and the theory of electromagnetism, which was famously formulated by James Clerk Maxwell in the 19th century. At its core, QED explains how photons, which are the particles of light, interact with charged particles like electrons. This interaction is crucial for understanding various phenomena, from the behavior of atoms to the workings of lasers. One of the most fascinating aspects of QED is the concept of virtual particles. In the quantum realm, particles can spontaneously pop into existence and then disappear again, a phenomenon that challenges our classical understanding of reality. These virtual particles are not directly observable, but they play a vital role in interactions between charged particles. For example, when an electron emits a photon, it can be thought of as temporarily exchanging a virtual particle with another electron. This exchange is what allows forces to operate at a distance, creating the attractive or repulsive forces we observe in everyday life. Another key element of QED is the idea of renormalization, a process that helps physicists deal with infinities that arise in calculations. When trying to predict the outcomes of particle interactions, some calculations yield infinite results, which are nonsensical. Renormalization is a mathematical technique that allows physicists to remove these infinities and arrive at finite, meaningful predictions. This approach has been incredibly successful, leading to predictions that match experimental results with astonishing precision. QED has not only theoretical significance, but also practical applications. It underpins many technologies we use today, including semiconductors and lasers. The principles of QED are essential for understanding how these devices work at a fundamental level. For instance, the creation of laser light relies on the stimulated emission of photons, a process that is deeply rooted in the interactions described by QED. One of the most famous experiments is the measurement of the anomalous magnetic dipole moment of the electron. This quantity describes how much the electron's magnetic moment deviates from what would be expected based on classical physics. QED predicts this deviation with incredible accuracy, and experiments have confirmed it to many decimal places, showcasing the precision of the theory. In addition to its successes, QED also raises intriguing questions about the nature of reality. The idea that particles can exist in superposition, being in multiple states at quantum information theory, is a fascinating field that merges the principles of quantum mechanics with information science, leading to groundbreaking advancements in how we understand and manipulate information. At its core, this theory explores how quantum systems, which can exist in multiple states simultaneously, can be used to process and transmit information in ways that classical systems simply cannot. One of the most intriguing aspects of quantum information theory is the concept of quantum bits, or qubits, which differ significantly from traditional bits. While a classical bit can be either a 0 or a 1, a qubit can exist in a state of 0, 1, or both at the same time, a phenomenon known as superposition. This unique property allows quantum computers to perform complex calculations at speeds unimaginable with current classical computers. For instance, imagine trying to factor large numbers, a task that takes classical computers a long time. Quantum computers, leveraging algorithms like Shor's algorithm, can do this much more efficiently, posing potential challenges to current encryption methods. Additionally, another important concept in quantum information theory is entanglement, where two qubits become interconnected in such a way that the state of one instantly influences the state of the other, regardless of the distance separating them. This phenomenon has sparked interest not only in computing but also in secure communication methods, as it lays the groundwork for quantum cryptography, where information can be shared with a level of security that's currently unattainable. Quantum key distribution, for example, uses entangled particles to create a secure communication channel. Any attempt to eavesdrop on this communication would disrupt the entangled states, alerting the parties involved to the presence of an intruder. Furthermore, the implications of quantum information theory extend beyond computing and communication. Researchers are exploring its applications in various fields, including materials science, where quantum simulations can lead to the discovery of new materials with unique properties, and in medicine, where quantum sensors could significantly enhance imaging techniques, allowing for earlier detection of diseases. As we delve deeper into quantum information theory, we also encounter the challenges it presents. Building a practical quantum computer requires maintaining the delicate states of qubits, which are easily disrupted by their environment, a phenomenon known as decoherence. Scientists are actively working on various approaches to mitigate this, such as error correction techniques and the development of qubits, which could be more interesting. The future of quantum information theory looks promising, with ongoing research pushing the boundaries of what we thought was possible, and as we continue to understand and harness wave function collapse. Often abbreviated as WFC, is a fascinating concept in quantum mechanics and computer science, specifically in the realm of procedural generation. At its core, the wave function is a mathematical function that describes the quantum state of a system, providing information about the probabilities of the outcomes of measurements. In quantum mechanics, when a measurement is made, the wave function collapses from a superposition of states to a single state, which is the outcome observed. This idea has intrigued scientists and philosophers alike, because it raises profound questions about reality and observation. The act of measurement seems to influence the physical state of a system, leading to discussions about the nature of reality itself. In the context of computer science, particularly in algorithms used for generating content, it is utilized to create complex and diverse patterns, textures, and even entire game levels based on a small sample input. The algorithm analyzes the sample, determining the relationships and constraints of the tiles or elements within it, and then generates new content that adheres to these learned patterns, ensuring that the output maintains a coherent and visually appealing structure. This method has been applied in various fields, including video game design, art generation, and even urban planning, where the need for organized and aesthetically pleasing arrangements is crucial. One of the most intriguing aspects of the wave function collapse algorithm is its efficiency in creating large amounts of content while still respecting the original style of the input. This is achieved through a process that resembles the quantum wave function collapse, where the algorithm explores possible configurations until it settles on a valid arrangement, effectively collapsing the possibilities into a final output. It combines elements of possibilities into a final S. But it doesn't just allow linear progress, it provides digressive opportunities from the source material, resulting in unique yet familiar designs. Moreover, the concept of wave function collapse also leads us into discussions about determinism and indeterminism in physics. In classical physics, one could predict the future state of a system if all initial conditions were known. However, quantum mechanics introduces a level of unpredictability, as the exact state of a quantum system cannot be determined until a measurement is made. This duality has sparked numerous debates about free will, the nature of reality, and how much our observations influence the world around us. Additionally, in the field of philosophy, the implications of wave function collapse touch on ideas related to the observer effect, which suggests that the act of observation can change the outcome of an event. This has led to various interpretations. Quantum phase transitions are a fascinating area of study in condensed matter physics, where matter changes its state not due to temperature but because of quantum mechanics, specifically as a result of changes in external parameters like pressure or magnetic fields. In classical physics, we think of phase transitions as processes that occur with temperature changes, like when ice melts into water or when water boils into steam. However, in the quantum realm, these transitions can happen at absolute zero temperature, driven by quantum fluctuations rather than thermal energy. This unique behavior is observed in certain materials, especially those that are strongly correlated, meaning that the interactions between particles are significant and lead to emergent properties that cannot be understood by just looking at individual components. One of the most intriguing examples of quantum phase transitions occurs in systems known as quantum magnets. In these materials, the spins of electrons can align in certain configurations, and as external magnetic fields are altered, the system can transition from one magnetic order to another, showcasing a complete change in its properties without any change in temperature. The concept of critical points also plays a vital role here, where at these points the behavior of the material changes dramatically, leading to phases that can exhibit properties like superconductivity or unusual magnetic behaviors. The study of quantum phase transitions not only deepens our understanding of fundamental physics, but also has potential implications for technology, especially in the development of quantum computing and materials that can conduct electricity without resistance at higher temperatures. Researchers are constantly investigating new materials, such as iron-based superconductors or certain types of topological insulators, to explore how these transitions can be harnessed for practical applications. A significant aspect of quantum phase transitions is the role of quantum entanglement, where particles become interconnected in ways that the state of one particle can instantaneously influence the state of another, regardless of distance. This entanglement may play a key role in the behavior of materials undergoing a quantum phase transition, potentially leading to new states of matter that could revolutionize our understanding of physics and material science. Moreover, the theoretical framework that describes these transitions often involves complex mathematics and concepts such as the renormalization group, which helps physicists understand how physical systems behave at different scales. This mathematical approach allows scientists to predict the outcomes of quantum phase transitions and to identify the conditions under which they occur, giving rise to a rich field of study that bridges theoretical and experimental physics. As researchers continue to dive deeper into the realm of quantum mechanics, quantum phase transitions remain a pivotal area. In the realm of quantum mechanics, the concept of spin is a fundamental property of particles. Much like how mass or charge is essential to understanding the behavior of matter. However, spin is quite unique and intriguing, as it doesn't refer to any literal spinning motion, but rather represents an intrinsic form of angular momentum that particles possess. Take, for instance, electrons, which are elementary particles with a spin of 1/2, meaning they can exist in one of two states, often referred to as spin up or spin down. This binary nature of spin is crucial, especially in the field of quantum computing, where qubits or quantum bits utilize the spin states of particles to perform calculations far more efficiently than traditional bits. When we talk about quantum states, we delve deeper into the idea that particles can exist in superposition, which means they can be in multiple states at once until measured. This principle is famously illustrated by Schrödinger's cat thought experiment, where a cat in a box is simultaneously alive and dead until someone opens the box to observe it. The measurement process in quantum mechanics forces particles to choose a state, collapsing their superposition into one definite outcome. This phenomenon is known as wave function collapse, and it raises fascinating questions about the nature of reality and observation. In addition to superposition, there's another intriguing aspect related to spin, called entanglement. When two particles become entangled, the state of one particle becomes linked to the state of another, no matter how far apart they are. This means that if you measure the spin of one particle, you instantly know the spin of the other, regardless of the distance separating them, which Einstein famously referred to as spooky action at a distance. This entangled state has profound implications for quantum teleportation and quantum cryptography, as it allows for the secure transfer of information without the need for physical particles to travel between sender and receiver. Moreover, the study of spin and quantum states has led to the development of new technologies, such as magnetic resonance imaging, or MRI, which relies on the principles of nuclear spin to create detailed images of the inside of the human body. The understanding of how particles behave at the quantum level has also opened doors to exploring new materials, such as topological insulators, which have unique electronic properties that could revolutionize electronics and energy storage. Researchers are even investigating the potential of using spintronic devices which exploit the electron's spin state to create faster and more quantum squeezing. Is a fascinating phenomenon that arises from the principles of quantum mechanics, particularly in the realm of quantum optics. To understand quantum squeezing, it helps to first grasp the concept of quantum uncertainty, which is famously described by Heisenberg's uncertainty principle. This principle states that there are fundamental limits to how precisely we can know certain pairs of physical properties, such as position and momentum, or in this case, the phase and amplitude of a light wave. In a typical scenario, the uncertainties in these properties are balanced, meaning that reducing the uncertainty in one property will increase the uncertainty in the other. However, in quantum squeezing, this balance is altered, allowing for a reduction in the uncertainty of one property without a corresponding increase in the other. This is achieved by manipulating the quantum state of light, often through a process called parametric down conversion, where a single photon is converted into a pair of entangled photons. The process can lead to situations where the amplitude of the light wave exhibits lower uncertainty, while the phase uncertainty increases, or vice versa. The result is a squeezed state of light, where one property is enhanced at the expense of the other, but the overall uncertainty remains confined within the limits set by quantum mechanics. Quantum squeezing has significant implications for various applications, particularly in the field of quantum information and quantum communication. For instance, squeezed light can improve the sensitivity of measurements in interferometry, which is crucial for experiments that detect gravitational waves. In these experiments, the enhanced precision provided by squeezed states allows scientists to detect incredibly tiny changes in distance, which would otherwise be obscured by noise. Additionally, squeezed light can also enhance the performance of optical communication systems, allowing for more reliable transmission of information over long distances. Moreover, quantum squeezing plays a crucial role in the development of quantum computers and other quantum technologies. By using squeezed states of light, researchers can create more efficient qubits, which are the fundamental units of information in quantum computing. This efficiency could lead to faster and more powerful quantum computers, capable of solving complex problems that are currently intractable for classical computers. The study of quantum squeezing continues to be an active area of research, with scientists exploring new methods to generate and utilize squeezed states of light, as well as investigating their potential applications across various fields. This area of research not only deepens our understanding of quantum mechanics, but also paves the way for technological advancements that could revolutionize how we process and transmit information. Decoherence is a fascinating concept that plays a crucial role in our understanding of quantum mechanics and how it relates to the classical world we experience every day. At a fundamental level, decoherence occurs when a quantum system loses its quantum properties, such as superposition and entanglement, due to interactions with its environment. Imagine a delicate wave representing a quantum state that disturbs the surrounding water as it moves. As time progresses, this wave's coherence diminishes, eventually blending into the larger body of water, becoming indistinguishable from it. This process is key to explaining why we don't observe bizarre quantum behaviors in our macroscopic world, where objects behave in ways that align with classical physics. The concept of classical emergence is closely linked to decoherence. Classical emergence refers to how complex systems and phenomena arise from simpler, underlying rules. In quantum mechanics, particles exist in superpositions, which means they can be in multiple states at once, but when we measure or observe them, they seem to collapse into a single state, a process that decoherence helps to explain. As a quantum system interacts with its environment, the coherence of the quantum states breaks down, leading to the emergence of classical behavior. This transition from quantum to classical is not merely about particles behaving differently, but rather about how our reality is structured, giving rise to the predictable, deterministic world we navigate daily. A notable example of this is found in everyday objects, like a spinning coin. While the coin is in the air, it can be thought of as being in a superposition of heads and tails, but as it lands, it decoheres, and we observe a definite outcome, heads or tails. This illustrates how, through decoherence, the quantum world transitions into the classical realm, where we can make sense of the outcomes we see. Researchers have explored various implications of decoherence and classical emergence, including the role they play in the interpretation of quantum mechanics. One interpretation suggests that decoherence provides a pathway to understanding why certain outcomes are observed and others are not, leading to discussions about the nature of reality itself. Some scientists argue that decoherence can explain the apparent randomness of quantum events, while others believe it might help bridge the gap between quantum physics and general relativity, potentially offering insights into unifying these two pillars of modern physics. Moreover, decoherence has practical applications in the field of quantum computing. Quantum computers rely on maintaining quantum states for calculations, but these states are vulnerable to decomp. Quantum entropy is a fascinating concept that arises from the intersection of quantum mechanics and thermodynamics, and it plays a crucial role in understanding the behavior of quantum systems. In classical physics, entropy is often associated with the amount of disorder in a system. However, in the quantum realm, things become more complex. Quantum entropy is generally defined using the von Neumann entropy, which is a measure of the uncertainty associated with a quantum state. This is similar to how classical entropy measures the disorder in a physical system, but it takes into account the unique properties of quantum states, such as superposition and entanglement. When a quantum system is in a pure state, meaning it can be described by a single wave function, its von Neumann entropy is zero, indicating that there is no uncertainty about the system's state. However, when the system becomes entangled with another system, or when it is observed, the entropy can increase, reflecting the loss of information about the original state. This increase in entropy is often viewed as a measure of the information lost to the environment, which is a key idea in understanding how quantum systems interact with their surroundings. One of the most intriguing aspects of quantum entropy is its relationship with black holes, which are regions of space where gravity is so strong that nothing can escape from them. The famous physicist Stephen Hawking proposed that black holes are not entirely black. They emit radiation due to quantum effects near the event horizon, leading to the concept of Hawking radiation. This radiation implies that black holes have an entropy which is proportional to the area of their event horizon, not the volume, challenging our classical understanding of entropy. This insight has profound implications for the nature of information in the universe, suggesting that information might not be lost when objects fall into black holes, but rather it is stored on the surface of the black hole, a concept known as the holographic principle. Moreover, quantum entropy is also a critical aspect of quantum information theory, where it helps in understanding how information is processed and transmitted in quantum computers. In this context, quantum entropy is used to quantify the amount of information that can be encoded in a quantum state, and it plays a vital role in protocols like quantum teleportation and quantum cryptography. Researchers are continuously exploring the implications of quantum entropy in various fields, including statistical mechanics and cosmology, seeking to unravel the mysteries of the universe and the fundamental nature of reality. In summary, quantum entropy is a rich and multifaceted concept that the quantum eraser experiment is a fascinating illustration of the strange and often counterintuitive nature of quantum mechanics. This experiment builds on the famous double-slit experiment, which demonstrates that light and matter exhibit both wave-like and particle-like properties, depending on how they are observed. In the quantum eraser experiment, researchers set out to explore the concept of which path information, which refers to the knowledge about the path a particle, such as a photon, takes when it travels through a double-slit apparatus. Initially, when particles are fired through the two slits, they create an interference pattern on a detector screen, indicating their wave-like behavior. However, if a measurement is made to determine which slit the particle went through, this wave-like behavior disappears, and the particles behave like classical particles, landing in distinct locations corresponding to the two slits, rather than creating an interference pattern. What makes the quantum eraser experiment particularly intriguing is that it allows researchers to erase the which path information after it has been obtained. In this setup, the photons are sent through a double-slit apparatus, and detectors are placed to measure the polarization of the photons, providing which path information. The experiment then includes a mechanism to manipulate this polarization, effectively erasing the which path information. When the researchers analyze the results based on the polarization state, they find that the interference pattern can re-emerge even after the initial measurement has been made. This suggests that the act of measurement does not merely determine the outcome, but rather interacts with the system in a way that can retroactively change previous results. This leads to profound implications about the nature of reality and observation in quantum mechanics. It raises questions about whether reality is determined at the moment of measurement or if it is a more fluid concept, influenced by the information available to the observer. In essence, the quantum eraser experiment challenges our classical intuitions about causality and the role of observation in shaping the physical world. The results suggest that information, specifically the absence of information, plays a critical role in determining whether we observe wave-like or particle-like behavior. This idea is further supported by theories in quantum mechanics that argue the observer cannot be separated from the observed, and the act of observation itself can influence the outcome of an experiment. As researchers continue to explore these phenomena, they uncover deeper layers of complexity in the foundation of quantum mechanics, further blurring the lines between reality and perception, and opening up exciting avenues for understanding. In the realm of quantum mechanics, time plays a fascinating and complex role that challenges our everyday understanding of how the universe operates. Unlike classical physics where time is treated as a constant, flowing entity, quantum mechanics introduces a more nuanced perspective. In this framework, time is often considered a parameter rather than a fundamental aspect of reality. This means that, in many quantum theories, time is something we use to describe how systems evolve, but it does not have the same kind of independence that we attribute to it in classical context. For instance, when we observe a particle, its position and momentum can be described by a wave function which evolves over time according to the Schrödinger equation. This evolution is deterministic, meaning that if we know the initial conditions of the system, we can predict its future behavior. But this does not imply that time itself behaves in a straightforward, linear manner. One of the most intriguing aspects of time in quantum mechanics is the phenomenon of entanglement, where particles become interconnected in such a way that the state of one particle instantaneously affects the state of another, regardless of the distance separating them. This raises questions about the nature of time and causality, as changes to one particle seem to occur without regard for the time it takes for information to travel between them. Additionally, there are interpretations of quantum mechanics, such as the many worlds interpretation, which suggests that all possible outcomes of a quantum event actually occur, each in its own branching universe. This leads to a radical rethinking of time, as every decision or quantum event does not just unfold in a single timeline, but spawns multiple realities, each with its own distinct progression of time. Moreover, the concept of time intersects with theories of quantum gravity, which seek to unite general relativity and quantum mechanics. In these theoretical frameworks, time may not be a fundamental aspect at all, but could emerge from more basic interactions at the quantum level. The idea is that, at the smallest scales, the fabric of space-time itself might be quantized, suggesting that time, as we perceive it, is a macroscopic illusion arising from the collective behavior of countless quantum particles. Researchers are exploring various approaches, such as loop quantum gravity and string theory, to better understand how time is woven into the very structure of reality. The relationship between time and observation is another critical topic in quantum mechanics. The act of measurement can alter the state of a quantum system, leading to the so-called observer effect. This raises philosophical quantum. Quantum biology is a fascinating field that explores the intersection of quantum mechanics and biological processes, delving into how the principles of quantum theory can influence and explain phenomena in living organisms. At the heart of quantum biology is the idea that certain biological processes, which we once thought were purely classical in nature, might actually involve quantum states and behaviors. One of the most intriguing examples comes from photosynthesis, where plants convert sunlight into energy. Researchers have discovered that during this process, energy is transferred through a series of molecules in a highly efficient manner, and this efficiency may be due to quantum coherence, allowing energy to travel simultaneously through multiple pathways before reaching its destination. Another captivating area of quantum biology is the phenomenon of avian navigation. Some species of birds, like the European robin, are known to migrate thousands of miles, and scientists believe that they may use quantum entanglement to navigate. Within their eyes, there are special molecules called cryptochromes that can detect the Earth's magnetic field. This detection is thought to rely on quantum processes, where paired electrons in these molecules become entangled, enabling the birds to sense directional cues based on the magnetic field's influence on their quantum states. Moreover, researchers are investigating the potential role of quantum effects in the sense of smell. The olfactory system responsible for how we perceive scents may involve quantum tunneling, a phenomenon where particles can pass through energy barriers. Some studies suggest that odorant molecules may interact with receptors in a way that involves quantum mechanics, allowing our brains to recognize a vast array of scents with remarkable precision. In addition to these examples, quantum biology also raises questions about the processes of consciousness and cognition. Some scientists hypothesize that quantum processes might play a role in how we think, feel, and experience the world around us. This idea is still highly speculative, but it opens up exciting avenues for research into the nature of consciousness itself. As we continue to explore the depths of quantum biology, we are only beginning to scratch the surface of how quantum mechanics might underlie the incredible complexity of life. The implications of these findings could lead to breakthroughs in medicine, technology, and our understanding of the fundamental nature of living systems. As researchers dig deeper, they may uncover more surprising connections between the quantum world and the biological processes that define life, transforming our perception of both biology and physics in the process. Quantum fuzzy logic is an intriguing and innovative area of study, combining principles from quantum mechanics and fuzzy logic, and it opens up new perspectives in how we understand and process information. At its core, fuzzy logic is a form of reasoning that allows for degrees of truth, rather than the traditional binary true or false. This is particularly useful in situations where information is uncertain or ambiguous, like in human reasoning, where things often aren't black and white. By integrating fuzzy logic with quantum mechanics, researchers are exploring how quantum states can represent fuzzy sets, enabling a richer framework for decision-making processes. In quantum fuzzy logic, the uncertainty inherent in quantum systems is embraced, rather than ignored. Unlike classical systems, where information is treated as precise, quantum systems can exist in superpositions of states, leading to complex interactions that can be modeled using fuzzy logic principles. For instance, consider a scenario where a quantum particle can be in multiple states at once. Fuzzy logic allows us to describe the probabilities of the particle being in these various states, incorporating the uncertainty into our calculations. This combination of quantum mechanics with fuzzy logic has the potential to enhance various applications, such as quantum computing, where it can be used to create more efficient algorithms that can process information in a way that reflects the inherent uncertainties of the quantum world. Furthermore, quantum fuzzy logic is seen as a promising avenue for artificial intelligence, allowing for improved reasoning capabilities in AI systems. By leveraging the unique properties of quantum states, these systems might be able to make decisions that account for uncertainties in a more human-like manner. Imagine AI that doesn't just follow strict algorithms, but instead can weigh options based on degrees of likelihood, adapting its responses in real time based on new information, just like humans do when faced with complex decisions in everyday life. Research in this field is still in its early stages, but the implications are vast, touching areas like quantum cryptography, where security relies on the principles of quantum mechanics. Here, quantum fuzzy logic could help in developing protocols that are not only secure, but also adaptable to the uncertainties in the environment. As we delve deeper into both quantum mechanics and fuzzy logic, the intersection of these two fields may lead to breakthroughs that redefine our capabilities in computing, data analysis, and even understanding complex systems in nature. Moreover, the mathematical foundations of quantum fuzzy logic build upon existing theories, incorporating elements like quantum probability and fuzzy set theory, which can be quite technical, but they ultimately serve to create a more robust framework for addressing problems that are. 2. Gravitational effects on quantum states is a fascinating topic that bridges the worlds of quantum mechanics and general relativity. At the heart of this area of study lies the question of how gravity, which traditionally operates on a macroscopic scale, interacts with the delicate and often counterintuitive phenomena observed at the quantum level. One interesting aspect of this interplay is the concept of quantum superposition, where particles can exist in multiple states simultaneously. When considering gravity, researchers have begun to explore whether the presence of a gravitational field influences this superposition. For instance, some theories propose that gravity could cause certain quantum states to collapse, leading to the idea that gravity might play a role in the measurement problem. A fundamental question in quantum mechanics concerning how and when a quantum system settles into a definitive state. Moreover, the idea of entanglement, another cornerstone of quantum physics, also raises intriguing questions in the presence of gravitational fields. When two particles are entangled, the state of one particle is directly linked to the state of the other, regardless of the distance between them. However, how does gravity affect this connection? Recent studies suggest that gravitational interactions could potentially introduce decoherence, which is the process by which quantum systems lose their quantum properties and behave more classically. This could mean that the very nature of entangled particles might change when they are subjected to gravitational forces, leading to new insights into both quantum mechanics and gravity. In addition, the concept of gravitational waves, ripples in space-time caused by massive accelerating objects, adds another layer to this discussion. The detection of these waves has opened up a new field of astrophysics, yet researchers are also investigating how these waves might influence quantum systems. For example, could the passing of a gravitational wave affect the coherence of a quantum state? Understanding this could have profound implications for both quantum computing and our understanding of the universe. One particularly intriguing idea that has emerged is the notion of quantum gravity, an attempt to unify general relativity and quantum mechanics into a single framework. Theories such as loop quantum gravity and string theory explore how space-time itself might have a quantum structure, suggesting that space and time could be quantized at the smallest scales. This could mean that gravity is not just a force acting on particles, but rather a fundamental aspect of the fabric of reality that interacts with quantum states in ways we are only beginning to grasp. Furthermore, experiments such as the use of atomic interferometers to test the effects of gravity on quantum states are ongoing. The measurement problem in quantum mechanics is a fascinating topic that delves into the very foundations of how we understand the quantum world, and it raises profound questions about the nature of reality itself. Essentially, the measurement problem arises from the way quantum systems behave, especially when we try to observe or measure them. In the quantum realm, particles exist in a state of superposition, meaning they can be in multiple states at once. Until we measure them, this is famously illustrated by Schrödinger's cat thought experiment, where a cat in a box is simultaneously alive and dead until someone opens the box to check. This paradox highlights the core of the measurement problem, which questions how and why the act of measurement causes a quantum system to collapse into one definite state, rather than remaining in a superposition of possibilities. Many interpretations of quantum mechanics attempt to address this issue. The Copenhagen interpretation, which was primarily developed by physicists like Niels Bohr and Werner Heisenberg, suggests that the act of measurement is what forces the quantum system to choose a specific outcome. According to this view, reality is not fully determined until we observe it, leading to the idea that our observations play a crucial role in shaping the universe. However, this interpretation has faced criticism for its seemingly subjective nature, raising questions about the objective reality of unobserved phenomena. Another popular interpretation is the many worlds interpretation, proposed by Hugh Everett III. This theory posits that all possible outcomes of a quantum measurement actually occur, but in separate, branching universes. Thus, when we measure a quantum system, we are simply becoming aware of one of these many outcomes, while the other possibilities continue to exist in their own separate realities. This approach eliminates the measurement problem by asserting that there is no collapse of the wave function. Instead, every potential outcome occurs, each in its own universe. Then there is the de Broglie bomb theory, also known as pilot wave theory, which offers a different perspective. This interpretation introduces hidden variables, suggesting that particles have definite positions and velocities at all times, guided by a pilot wave. In this view, the reality of quantum systems is deterministic, and the apparent randomness of quantum events is a result of our ignorance of these hidden variables. This theory provides a clear mechanism for how measurements yield definite outcomes, but it departs from the conventional understanding of quantum mechanics. The question of how consciousness interacts with quantum mechanics has also emerged as a point of contention.